Welcome to Brain Vision.
Okay, guys. So problem 7.57 asks us to solve the problem where we have a 0.200 kilogram box that starts at point A and slides down this quarter circle and then slides a distance dBc from point B to point C where it comes to rest. So the particle starts at rest at point A, has speed VB at point B, and then is at rest again at point C. So the first thing we're asked to do is solve for the coefficient of kinetic friction on the horizontal surface, which is from B to C. And then the second thing we're asked to do is find the work done by friction from point A to point B as the box slides down this quarter circle. Okay, we're given, of course, as I said, that VA and VC, the velocities at points A and C, are 0. VB is given as 4.8 meters per second. The mass, as I said, was 0.200 kilograms. The radius of this quarter circle right here is 1.60 meters, and the distance from point B to point C is given as 3.00 meters. So let's start by writing down Newton's first law. So Newton's first law says that the net force in the x direction, since we're on a horizontal surface, we only need to consider one dimension. The net force is equal to the sum of the forces acting on the box as it slides. Now, we can talk about gravity and the normal force, but we are not interested in those. We're only interested in the forces acting in the horizontal direction. And in this case, the only force that is acting in the horizontal direction is the force due to kinetic friction. Okay? And we can express that force as the coefficient due to kinetic friction, mu sub k, times the normal force. Okay? And there's a minus sign here. The reason the minus sign is there is, of course, because as this box slides, we want the force to act in the opposite direction of the motion so that it actually slows down, which is what friction does. So the normal force we know is equal to minus Fg. So if we plug that in here, we get positive mu sub k Fg. And of course, we know that the force due to gravity is equal to minus mg. So we get this expression. Okay. So now we want to relate this to the change in kinetic energy as the box moves from B to C. So we know that for any system that we can have, that the change in kinetic energy is equal to the work done by non-conservative forces, okay? Work done by non-conservative forces minus the change in the potential energy of the system, okay? So let's look at this term for a second, the change in potential energy. We know that the box is moving on a horizontal surface. The only source of potential energy in this problem is gravity. So if the height of the box is not changing, remember gravity is pointing down this way, okay? If the height of the box is not changing, then the potential energy cannot change. So for part A, we're going to let delta U go to 0, okay? And then our work done by non-conservative forces is equal to our work done by friction. Okay, so I will write that this is the work done by friction. Okay, so now we have that the kinetic energy is equal to the work done by friction, the change in kinetic energy. So I know that the work is equal to the force times the distance. Well, I know the distance is this distance BC, and it's equal to 3 meters. So I write the force, which we have written already as minus mu sub k mg. I write minus mu sub k mg times dBc is the work done. Okay? And that is equal to the change in kinetic energy, which is equal to 1/2 times the mass times the speed at c, okay, minus the speed at point B. Okay. Now, I'm told that the particle is at rest at point C, which means that this velocity is 0. So I'm going to go ahead and mark that out as 0. Okay. And then what I have is minus 1/2 m VB squared here, and minus mu sub k mg dBc here. I can cancel out the minus signs and the m on each side, so that what I'm left with is that mu sub k, and dividing both sides by g times dBc, I get that mu sub k is equal to VB squared over g dBc. Okay? And then if you plug in the numbers, the VBC, of course, g is going to be equal to 9.8 meters per second squared, as usual. And then our dBc is given us 3 meters. What I get when I plug that in is 0.392. Okay? That is the coefficient of kinetic friction on the horizontal surface. All right. Notice that this is a unitless quantity because we multiply mu sub k times the normal force in our equation, and that is equal to the friction force. So we have force on one side, force on the other, so this constant needs to be dimensionless. Now, the next part, in part B, we're asked to calculate the work done by friction from point A to point B. So again, I'll draw the quarter circle here. Here's point A. And point B. And remember that our radius was 1.6 meters, 1.60 if we're considering significant figures. So, and then of course my speed VB is the same as it was in the last section, so that's 4.80 meters per second. Now, I'm going to go back to the equation that related the work to the change in energies. So I have that delta K is equal to the work done by friction, which is our non-conservative force again in this case, minus the change in potential energy. Now, in the last section, because we were moving on a horizontal surface, the height stayed the same, so we were able to neglect this term. But this time, obviously, that is not the case, because we start at the top of this quarter circle and move down the slope, like so. So, we're going to have to calculate the height at these 2 points. We can go ahead and assume that B, position B, is at a height equal to 0. Okay, so height B is equal to 0. Now, let's expand this equation a little bit. I have the change in kinetic energy, 1/2 m times the square of the speed at B minus the square of the speed at A. Okay, and this is equal to the work done by friction minus, and the potential energy due to gravity is given by mg, and then the change in heights. So we go to hb is our final height minus ha is our initial height. Okay. All right, so I am told that the velocity at A is equal to 0. So we're going to go ahead and get rid of that term, set it equal to 0. And I know that the height at B is equal to 0. So I do the same thing here. Now I need to figure out what the height at A is. But if we look at this quarter circle, it's easy to see that the height of A, this distance here, is really just equal to the radius of this circle. Okay, so we put r here. Okay, now if I subtract or add this term to both sides, what I'll end up with is that the work done by friction is 1/2 m vb squared, excuse me, there, and then minus mg times the radius. And that is our expression for the work done by friction from A to B. And if we plug in all our numbers, we know the mass, the speed, we know gravity, and we know the radius. What we should end up with is negative 0.832 joules of work done. And that is our answer. Now, this should make sense because we know that friction works in the opposite direction of our motion, as I've said. So we would expect it to do negative work. Okay. Thank you guys for watching. I hope this was helpful, and we will see you in the next problem solution. Bye.